Hey guys, did you start working on some project for this class? Or I'm just asking because I want to understand if we will meet on Friday or not for several project presentations. Uh, but on maybe Monday. So um, I will send an announcement. Yeah, and ask if you want to present your work. S- So, the plan for today and Wednesday is to talk about text-to-speech problem. Um, so how to generate speech from or music um, from text or from some information about pitch, for example. And yeah, let me finish first with speech to text, because I mentioned the Whisper model, which is used at RIT for speech recognition. So it's just good maybe to know the architecture. Um, so it's the encoder-decoder model. So we have encoder in um, the speech features. In this case, spectrogram is used, is the input to the encoder, and decoder uh, provides the tokens, the speech. So, oh, the words. So this is encoder-decoder model. And today we will talk about different process, how to generate sound from the words. And um, the standard approach is uh, you have the text to generate a spectrogram, but there is a problem with spectrogram is that we can't convert it directly to waveform. And let me explain the reason. Um, so where's our notebook? So when we applied Fourier transform to audio file, I mentioned that it's complex, it returns complex numbers. So in Python, before um, current version of Torch, they didn't have complex numbers, and they created two channels, one channel for imaginary part, one channel for real part. Currently, Torch supports imaginary numbers. If you just write 2 plus 1 I believe, let's see. Um, if you just write, for example, 2 plus 1, I don't remember, I or j times 3, let's see. Yeah, then j. Then it will save this as complex number. So it just to mention because sometimes if you use like old models, you will get an error that you have two channel tensor because currently complex numbers are stored as one channel tensor. So and we talked last time. Um, let's upload some audio, for example, this music, or maybe it's better to upload some speech. When we visualize, this spectrogram, we actually visualize the absolute value of this Fourier transform, not the complex number. We can't visualize complex number. And if you create a spectrogram, um, you lose the information about imaginary parts. So that's why you can't convert directly back the spectrogram to audio file. If you would have the original Fourier transform, yes, then you can reconstruct audio. But if you have only absolute value, I will show you how it will sound if you just convert the spectrogram back with inverse Fourier transform. Um, so okay, 0.13 for example. Okay, so upload audio. So this is our audio.
Then in the same operations with ugly ones. Then in the same operations.
Um, so we apply Fourier transform. And then we can apply inverse Fourier transform. I think I have this code below. It's T. Reconstruction. Uh-huh. So this is the reconstruction. Let's see. I'm using the waveform as input. Now let me STF, create STF. Um, so in inverse, Mhm. I apply inverse Fourier transform to FFT. But mhm. But if we first take just absolute value uh, and apply inverse Fourier transform, it will sound as follows.
Then in the same operations with ugly.
Oh, no, wait a second. Uh, it sounds. Oh, maybe because I should import this function again. Hmm, let's see.
Then in the same operation.
Looks like it's. I should use the. Let's see. Mhm. Let's see if inverse STFT the built-in function will work. STFT. So first we create STF and then we apply inverse.
Then in the same operations with
Okay.
ugly one.
And now if I take the absolute value, let's try to do this here. It requires a complex value input tensor matching. Okay. Then it's maybe easier just to copy paste my function. Or I had to restart the kernel. Um, okay, now it should work. So if we lose information like about imaginary part, then we can't reconstruct this signal. So it sounds very robotic. um, so this is the problem that we want to solve because, yeah, we can generate the spectrogram from text, but then we should also be able to reconstruct it to waveform because spectrogram is just the um, magnitude of this Fourier transform, not the, it doesn't have which, this imaginary part information, which is called phase of the signal. We have only amplitude. So, to reconstruct this spectrogram, there was a well-known method which is called Griffin-Lim algorithm from 70s, and it was used before neural networks, which could but that algorithm works only on spectrograms before compression. It doesn't work for meal spectrograms. So again, the same problem. We can create the spectrogram from text, meal spectrogram, but um, we should well, you can upsample this meal spectrogram to the shape of spectrogram and apply this Griffin-Lim algorithm. It will work with some loss of quality. But in 2017, the first neural vocoder was uh, proposed. It's called WaveNet. And we will, so this was the first autoregressive model, similar to GPT model that generates um, this thousands of samples per second for the waveform. So before we will go to vocoder. Let me introduce just how we can generate the spectrogram from the text. And actually current models, they all use the same idea as that WaveNet. So if you understand that model, then you will understand all the current models like DiffWave. Well, there are some non-autoregressive also vocoders which are using GANs, like Hi-Fi GAN, but the high quality, the diffusion-based vocoders, they have high quality. Okay. Yeah, so as you remember, so this is the general pipeline. Uh, we want to generate a waveform from the text. There are some models that generate waveform directly, but most models they generate first spectrogram, meal spectrogram, and then apply vocoders to convert meal spectrogram into waveform. At least they have higher quality. So how to generate these, and a spectrogram is just an image. How to generate this image, and you remember every frame corresponds to a chunk of audio, and the values in this frame, they correspond to the frequencies in this prevalent in this chunk of audio. So also in 2000, oh sorry, WaveNet was proposed in 2016. In 2017, the first neural text-to-speech model was proposed, Takatron. And this is this is Takatron 2, the second version of Takatron. So the input is normalized text. You remember normalized, it means that uh, cleaned the text like the standard pre-processing, maybe um, and I don't know if they use some staging. So then the text was transformed into phonemes. So there are like lookup tables how to transform a given word in, for example, in English language to phonemes. And let's see if I have the illustration. No. The illustration of the difference between graphemes and phonemes. Maybe it's in this presentation. Yeah, so like we have a word. It's represented by graphemes, the characters, but then you can map them to phonemes. And the problem with, for example, English language is that the same character or syllable can be represent a different phoneme. But there is a model you can Google. It's called G2P, grapheme to phoneme, and it will represent your input text with phonemes instead of graphemes. So this is the first pre-processing step. After we get the phoneme representation of our text, we can apply embeddings because the number of phonemes is just a fixed dictionaries. We can create embeddings, and these embeddings we will use as input to our text-to-speech model. So after that, based on these phonemes, our model will generate this spectrogram, because each phoneme has its own pitch. For example, there's a lot of research. Different vowels, they have different pitch, different height, and also it depends on the male or female voice. But it can give you an idea that if you know phonemes, actually before neural networks, it was called concatenative speech generation. They just recorded these phonemes and then they just added these frames in spectrograms, these phonemes, and then applied backorder. So like in this Big Bang theory, Hawking is using this speech generation device, and it sounds robotic. So, because at that time they used this is called concatenative speech synthesis. Yeah, and then after we have this spectrogram, we can apply another neural network model, vocoder, that will convert it to a signal. So there are some ideas why we use spectrogram. So the first point is that we can kind of separate two tasks, like converting spectrogram to waveform is one task. It's called vocoder. Representing text by spectrogram is another task. So kind of different modules. Also, spectrograms, they kind of preserve the frequencies representation, and also it's a compressed version of the standard spectrogram. As you remember, we use this logarithmic scaling and into matching into bins. Okay. And also, yeah, it's much less data uh, than in wave form. So this is the idea of this Takatron model. Um, we have input text, then extraction of phonemes, then some convolution layers, and at that time there wasn't transformers. Now, of course, nowadays we use transformer models. At that time, they used like you remember for translation, we used two LSTMs with attention. So um, at 2017, also this paper, Attention is All You Need, appeared. And they applied this attention in this model. So uh, attention between spectrogram frames and phonemes, the embeddings of phonemes. And so this recurrent neural network was used um, to process phonemes, embeddings of phonemes. And this recurrent neural network was used to predict the next frame of the spectrogram. And there was, well, it's local attention because they looked only at the previous spectrogram frame. And then they predicted two vectors. One was the new frame in spectrogram, another was the classification token if we should stop the generation of the spectrogram or if we should continue the generation. Um, and yeah, why we need the information about the previous frame? Because typical speech is continuous, so to get smoother transitions. And also this prenet was used for the same reason. Kind of in our recurrent neural network, we also looked at the previously generated frames. And this is the loss. So this should be prenet, postnet, and stop token. Stop token is using cross entropy loss because it's classification task. So I don't think we should look at all the details. Yeah, this is the local attention explained that we look at the previous embeddings of previous frames. Um, aha. So also they used another trick, which is called guided attention. So the first column represents training without attention, the second with is guided attention, and you can see that after how many iterations? 100,000 iterations without attention, without this guided attention, the um, attention didn't learn well this diagonal structure, but with guided attention it learned better. So there was a trick. which introduced some weights on, like higher weight on the diagonal elements and lower weights on the off-diagonal elements. This is not modification of this attention. And this is the kind of next modification of the stackatron. It's called GST. They added also style of speakers. So they also added attention on the style, uh, like to create a sad or happy voice and so on, or maybe different speakers. Yes, then they added also different speaker encoder. But let's maybe. So in other models, they generate, for example, embeddings instead of. You remember last time when I demonstrated this voice conversion, we used vector embeddings instead of spectrograms. So there are models that generate the vector embeddings. So fast speech, it uses GANs. It's not autoregressive model. Um, let's see if we have. No, I don't have it here, but there are models like Valia, like DALI. There's Vali that generates actually uh, vector embeddings. But still, after we have these vector embeddings, we should convert them into audio in the waveform. So again, we should use vocoder. So there is another model which uses codecs natural speech too. But again, it generates just embeddings, the codecs. And again, we need to use them to generate actually the waveform. And yeah, I want to talk about this model, which is called WaveNet. The first model that generated the waveform from spectrograms, but now we can also apply it on the vector embeddings, and it will generate waveform just based on the vector representation instead of spectrograms. So WaveNet. I believe, yeah, it's from DeepMind. I believe they still have the the page with presentation. So I think you have seen this image. It's called um, causal convolution. We will talk about this now. Later, people use this causal convolution for time series predictions because in time series you also want to predict the future time stamp based on the previous history. And if you will work with time series forecasting, there is a model CNN RN LSTM, so convolutional and recurrent neural network. So they use this dilated causal convolution and then apply LSTM. And yeah, they generated audio. So they trained this model on music instruments and on the speech. I didn't see music instruments now. They had examples of this model trained on piano. And it just generated some piano music, but it didn't sound actually uh, musically nice. It just generated it was changed just, and the same with voice. It generated something like similar to speech, but um, of course it was it's called not eligible. It was yeah, it didn't make sense. It just sounded as speech. But when we conditioned this model on spectrogram, then it generated the audio which was encoded by spectrogram. So this was the main application to generate this, to apply this wavenet, but conditioned on spectrogram. Nowadays, we condition on this vector representation of audio. And then it generates coherence sound, not just random samples. Okay, so I prepared a notebook with implementation of this wavenet. And again, this it's maybe useful to understand this model just because this convolution is used also in other models like time series forecasting. So not only for speech. Well, and actually it's interesting that I think I have it open. Yes. That when we were talking about speech processing, we always used some NLP, like large language models for transformer models, models from NLP. Then for images, we used some models from image processing, like CNN, convolutional neural networks. But at least there is one architecture which was developed specifically for speech, which is used in different applications. So, okay, the first building block is causal convolution. As you remember, the when we apply convolution, then we convolve, like, for example, with kernel size 3, we convolve these 3 points in 1, then we convolve these 3 points in 1. But we kind of look ahead when we apply this convolution. How to uh, force our convolution layer only look at the previous data? The answer is very simple. Add padding from the left. If you add padding from the left side, for example, I add 2 zeros here and apply convolution like that, then I will predict this token, for example. Then I shift my window and apply convolution. Let's see. Oh, actually, no, I will predict this point. Then I shift, and then I will use these 2 blue points to predict the next one. But you can see that we didn't use the future tokens, the future values. And if you continue this process, every new embedding, or what's called vector, will be generated only based on the previous information. And this is called causal convolution. After that, we also apply dilation. It's called dilated convolution, because we skip here every second, then we skip 3, then we skip 7, and so on, like power of 2. Uh, um, because audio, you remember, it has a lot of data, and this dilated convolution allows to look at the like more data behind, as it's called receptive field. So to increase this receptive field, they propose to also to use this dilation. So, do you have any questions about this causal dilated convolution? So, yeah, we add padding, then we convolve, then we like on the next step, we again use this filter, but now let's see, like this, because now we will skip these points, and if our kernel size is 3, then we actually will look at 5 points. Then we will skip um, 3 points, so our kernel will have the same size, the same dimension 3, but we will kind of look at what's the number of points. It will be 6, 9. Then it will look at 9 points and so on. And if we apply this, for example, 8 times, then the receptive field will be about 200 something points, which is about I can be wrong, about 10 or 20 milliseconds of audio. And then we generate a new token. So we want to predict a new so if you think about waveform, we want to predict just the next value of our waveform. And we should do this 16,000, or in this case, I don't remember, 16,000 or maybe 22K times, just for to generate 1 second. And our ground truth will be shifted by 1, like in GPT model. It's autoregressive model. The ground truth will shift by 1 sample, and we will train our model such that it will map a new sample to the next sample of the ground truth. Okay, now let's look at the code. Oops. So, yes, if we have inputs size L, we add m minus 1 zeros from the left, and then we apply the standard torch conv 1D, torch convolution. But it will work as causal convolution because of the padding. Here is just an example. If we create this array of 10 numbers, then we add padding, and kernel in this case is just of size 2. So we add 1 0 from the left, and then we convolve. If our kernel has values 1, we will multiply 0 by 1, 0 by 1, add them together, and this is the result of the first convolution. Then 0 times 1, 1 times 1, it will result in 1. Then 1 times 1 plus 2 times 1, we convolve with this kernel. We will get 3, and so on. But the output shape will be exactly the same, 10 numbers. Because you remember, if I apply convolution, the resulted shape is smaller by the kernel size minus 1. So this is how this causal convolution works. And here is the code example. So we pad kernel size 3, so this is example with dilation. This is an example I did with dilation, because if we skip every second sample, then we will need to add more zeros in front of our input. So that's why here I add 4 zeros instead of 2. And then we apply the convolution, but with dilation. I don't know why I used the kernel with these numbers, 1, 1, negative 1, but this is the result. So first we apply this filter to these 3 zeros, and the result will be 0. Then we apply to these numbers 0, 0. Oh, wait, not to 3 zeros. We skip every one, to 5 zeros actually, because so we skip the second one. So 1, 2, 3, 4, 5. Yes, and the result, and we multiply the first element by 1, the third by 1, and the fifth by negative 1. Then we kind of shift this frame or box, and then we multiply this by 1, this by 1, and this by negative 1. And the result, as the result, we will have negative 1, and so on. So it's just to give you an idea how dilated convolution works, because it's one of the main notices and in this model. Okay. And then here is this class implemented. Well, actually, here is the paper. We have just 1 minute left, but we can continue next time, because it's still the state-of-the-art model. Well, they added diffusion, like multiple steps. They increase the speed of generation, but the idea is the same. Yeah, so this is how this entire model looks like. We use causal convolutions, dilated convolutions, And uh, because they didn't know attention, they used kind of earlier version of attention, like one path multiplied by sigmoid function, which kind of takes values 0 or 1, so it kind of makes this signal smaller or last pass. And then by one convolution, skip connection, and then they predicted the one sample of these thousands for the waveform. Yeah, so this is the next building block, the gate activation unit. But let's continue next time.